Hello everybody, my name is Stoynov and my group is working on DNA damage response and how to find out, and we'll try to find out more rational anti-cancer therapy using our knowledge in DNA damage repair. During the cell lives for 24 hours, the DNA of the cells obtained more. They say that it's okay.
It's okay? Okay.
Yeah. The DNA of the cells obtain more than 70,000 different DNA damages that have to be repaired in order to maintain genomic stability and prevent cancer. Okay, the extensive study of the DNA repair revealed several DNA repair pathways, and more than 300 proteins are involved in these pathways. The extensive study revealed actually the biochemical mechanisms and the protein-protein interactions of this DNA damage response. However, what is missing actually is a precise time frame of the recruitment and removal of the protein participating in DNA damage repair. Therefore, our goal, the goal of our group actually, is to measure precise kinetic of the recruitment and removal of DNA repair factor and complex DNA damage, DNA lesions. For this purpose, we use transgenic Kyoto cell lines, which actually express EGFP tagged protein under control of their own regulatory sequences. We use UV laser microirradiation to generate DNA lesions in precise three-dimensional volume. Unfortunately, the movie is not working. But anyway, we succeed to obtain more than the precise kinetic of more than 70 proteins which participate in DNA damage response. We model them using developed from us consecutive reaction change model, which represents the kinetic of the proteins like several consecutive reactions which are required for the recruitment of the proteins, the time from which the proteins stay on DNA damage to DNA lesions, and the kinetic of the removal of the proteins from the site of DNA damage. However, some of the proteins have more complex kinetics, which is due to the fact that they are recruited from two or more different ways. Such proteins is let's say HTLF proteins, which we can model with two different CRC actually models, and we can reveal the kinetic of all these two reactions using this CRC model. The same is the case with PARC1 proteins, which we can fit to two different CRC models. In this way, we model the kinetic of the 70 proteins which are recruited on the site of DNA damage. After that, we hierarchically cluster them in seven different clusters. And after that, we combine this information with the protein interactions which is available for these proteins to generate temporal map of the protein interaction during complex DNA damage repair. And this information actually reveals several master regulators which interact with most of the proteins during different time points, such as PARC1, which interact with the proteins, with most of the proteins in the first two clusters, and PCNA, which interact with the proteins from the 3rd to 5 clusters, and ubiquitin, which interact with the most of the protein between 5th and the 6th clusters. And the last are proteins which participate in DNA, actually in the resection of DNA damages in the homologous recombination. This is the map actually of the recruitment and association of the protein to DNA damage sites. And what we can find actually is that protein which participate in the replication error-free DNA replication are coming 60 seconds earlier than protein which participate in replication of error-prone DNA replications, which found that this gives 60 seconds windows of opportunity of cells to repair DNA damages without errors actually. Okay. When we have such a resource from the kinetic of the recruitment removal of these proteins, this could be the kinetic-based platform to investigate the systematic impact of anti-cancer drug targeting DNA repair pathways in vivo. And that's why we test one PARP inhibitor, talazoparib, which is also powerful anti-cancer drug. And what we see that PARP inhibition actually leads to dramatic rearrangement in the order of the recruitment of the repair proteins, altering coordination and the outcome of DNA damage repair. As you can see, some of the proteins are not recruited anymore, and some of the proteins are rearranged. Most of them are delayed. This is particularly, you can see this for the protein like PCNA and protein which participate in the error-free DNA replications. They are delayed with more than 100 seconds, and in this case they come together with the protein with error-prone, which participate in the error-prone DNA replication. This means in this case you don't have these windows of opportunity to repair DNA without errors. In conclusions, we generate the first comprehensive kinetic-based DNA repair resource encompassing the precise kinetic of 70 DNA repair protein that reveals the detailed temporal map of the protein interaction during complex DNA damage repair. Treatment with PARP inhibitor causes dramatic rearrangement in the order of the recruitment of the repair protein that can change the mechanisms and the outcome of the repair process and contribute to their anti-cancer activity. We generate actually interactive site, and everybody actually can check the kinetics and the mathematical models and the videos from our study. The most difficult part in such study to study kinetics is actually to measure the kinetic of the recruitment, and this is because actually the cells are moving. You cannot see this because the movies are not working. Anyway, the cells are moving a lot. That's why the measurement of the kinetic of the recruitment is difficult. That's why our group developed special software for image analysis, which help us to measure such kinetics. And now I will invite Georgi actually to present his software, because I think it's really important in this workshop people to see how the things are done.
Well, good morning, everyone. Can you hear me for this microphone? Yeah, it's okay. So I will need both of my hands to demonstrate our software, and I will free space for the mouse. So this is the interface of our software. Oh. Okay, now must work. Yeah, it's okay. So this is the interface of our software. If you look to the left, you can see a file browser dialog that can be used for easy access to the images. So from here, you can open the images, you can rename them, you can copy, paste, and move through the directories. And you can, as I said, you can open the images from here. And now I'll open one video. So in the center screen, you can see our image. This is an image obtained from spinning disk confocal fluorescence microscope, and this is actually a time stack which means that this is a video that is recording what's happening with our cell during a one-time window. And as Stoyno just said, you can see these points here are actually the place where our protein is recruited. What are we actually seeing on this image? This is how a Kyoto cell line that is stably transfected and expressing a protein that is nuclear localized. This RNF 168 is protein that's required for the DNA repair. And by measuring the kinetic of recruitment at this discrete zone of the cell, we can obtain a kinetic, how the protein recruits and how it works at the site of DNA damage. But first, why the protein is recruited at this site? We're using ultraviolet laser to actually create, to actually apply. So we're applying ultraviolet laser at the discrete zone of the nucleus, and in this zone we are generating complex DNA damage. And the protein is actually recruited to repair this damage. And moreover, what is important for this image? If we analyze the pixels that are on this image, we can analyze the intensity value of these pixels. As higher is this intensity, as the protein concentration at that discrete zone of the nucleus is higher. So this means that if we measure how much is the intensity in the zone where the protein is recruited, we can actually obtain the concentration of the protein in this zone of the nucleus. So this image, this video is not only a time stack, so it is also on a Z stack. What does this mean? We have 3 focal planes that are captured in the same time from our microscope. And why we are doing this? If you look at this spot, this is actually a spot that can move not only in XY direction, it can move also in Z direction. And to be sure that this foci will be on our plane, we're actually capturing 3 planes at a distance of 0.5 micrometers. And after we're applying, so now I will apply an algorithm that will create a result image by using maximum intensity projection. What we will do now, we will create from the whole Z stack, we will create one frame, and for each pixel, we will take the maximum intensity of the pixel from the whole Z stack. And like this, we'll improve a bit the intensity. So this is actually generating a bit much more noise, but at least we are sure that our foci are in the plane that we are analyzing. So now we need to extract the numerical information from this image, and how we will do this. For that purpose, in our software, we have different types of regions of interest. If you look at the top screen here, you can see the different shapes that you can apply to our software. So you can draw, for example, rectangular ROI, you can draw oval shape ROI. This type of polygon is a bit difficult here. And also this one here. More interestingly, we can use also something that we call a stacking ROI. This is something new, and in other software you cannot find such a thing. If you look at this, we actually have here a stack ROI, and we can change the number of stacks. For example, I will put here 5. So what we can measure here, we can measure actually layers, which is very important if we want to capture some structures like waves or something like this in the cells. You can apply this also for the oval ROI and for all types of ROI. For example, this one and this one here. So, more interestingly, we have developed a different type of ROIs, because now I will clear all the ROIs and I will show you. If we try to measure directly the foci, for example this one, if you look carefully, you can see that the foci actually escapes our region of interest. So this is a problem. The cell is moving. This one here is not moving very rapidly, but in some cases the cells can move throughout the whole field. So we need to be able to somehow analyze the image, to segment the image in order to classify the pixels in different regions based on some property of the pixels. In our case, the best way is actually to use the intensity as a criteria for the classification. And because of that, we imported in our software an algorithms for segmentation. But first, if you look at the image, you can see this. There is a lot of noise around the whole image. So to improve the quality of the segmentation, we need to apply some filter in order to smooth the image, to make the regions more easy to be found by the algorithm. If you look at the two images, on the left you can see the raw image, on the right will be the smoothed image. Our software have many different filters. For example, here are the different filters that can be used for smoothing. I will apply Gaussian blur, 5 to 5 size of the kernel. And if you look, you can see that, I hope that you can see, the little noise here is disappearing. So you can apply also different filters. You can apply filters to sharpen the image. You can apply filters to detect some gradients. For example, here we have Sobel operator, gradient detectors. But now we will concentrate on the workflow that we are using to obtain the kinetics that Stoyno just showed you. So the next step is actually to apply a segmentation. I will use one-dimensional global threshold for the segmentation. What does this mean? If you look at this image here, I'll make it a bit bigger. So if you look at this image on the right here, this is actually a histogram. This is showing how the distribution of the pixels, so how much is the number of pixels with specific intensity. So on the left, you see the pixels with 0 intensity, and on the x-axis, you are moving to the right, and you are seeing the pixels, how much pixels with different intensity we have in the images. So basically, if we analyze this histogram, we can create a threshold that can distinguish the foreground from the background. And here is the histogram of the smoothed image. If you look at this, you can see that we can clearly distinguish two types of pixels in the image. So the algorithm will automatically detect, as you can see, the two types of pixels, and it will put a threshold that will distinguish the two types of pixels. So now we will check. This was with only one threshold, but we have also foci on the image, so we will need a second threshold. By this, we can distinguish also the foci that we are interested in. So now we have artificially computer-generated segmented image that can easily be, we can easily further analyze it. For that purpose, we will use something unique also for our software, something that we call the tracking array. You can enable this from here on the menu there. And the only thing that you need to do now is just to press on the spot that you're interested in, and it automatically generates a region of interest. And if we move a bit the view, you can see that this region of interest now tracks the spot and measure what is happening there. Also, something unique for our software is that we can actually measure in real time what is happening to that foci. Now I will select the other one here and the other one. And the other one. So now we have 4 foci that we can further analyze. They are measured, and what we can actually see on this chart here. I will disable this now. So on this chart here, we can change what is visualized on the X and on the Y axis from here. You can specify what to be the XY value, so we can check the test slice. This is the exact number of the slice from which the intensity value is extracted, or we can specify a second or a minute or a time. Yeah. I will use tsec, so the XY axis now will be set to time in seconds. On the y-axis, you can specify different type of measurement. You can measure the area of the region of interest, you can measure the mean intensity value of the pixels inside the region, and also the minimum, maximum value, the total intensity inside, or even you can apply some custom-made functions. So, maybe you're wondering why I'm using stacking ROI for these measurements here. These lines here are actually our foci, and this one here is the intensity of the peripheral circle of our region of interest. We will use this information from the peripheral ROI actually to normalize the result, because we need the value to be starting at 0 to be able to mathematically model it. And because of that, we will apply a function that now will use the information to calculate by using this formula. I will open it a bit bigger to be able to see what we're actually doing. So the formula that we just applied to our data set is actually this one here. So you have the mean value of the central ROI. We subtract from this value, the mean value of the peripheral ROI, and after we are subtracting the same this value, but for the exact 6th frame. This is the frame exactly after the micropoint irradiation. So why we do this? We do this to normalize the effect of the laser photobleaching, because when we apply the ultraviolet laser, it creates a bit of a little photobleaching, but it's still there. So if we don't use this here, it will start from different. It will not start exactly from the 0. And when we calculate this for each frame, we apply to the area of the region of interest. So this formula here returns the total intensity, so the total amount of the protein that is presenting in the region of interest. So now we have measured this image, and we can export directly the information to tab delimited text files. Just pressing Auto Export, and the files will be automatically generated, and all the information from the image will be stored in numerical values. So to this point, we just analyzed our first image, and now we can create something that we call protocol. I will call it protocol 2. And we have an option to store actually all the settings that we obtained now for the analysis, so the segmentation values, the tracking parameters. And we can store them, so the filters also, the spot detector values. We can store them here, and we can apply them automatically to the next image. So all of these steps that I just do, you don't need to do it for every image. Because if we're analyzing more repeats of the same experiments, the cell types, the cell intensity is similar. So all of this can be applied automatically. Just you need to press protocol 2, and the computer automatically will analyze the whole image. And if you look here, yeah, I forgot to do something before. Yeah, you need because here is Z-stack. You need at least to make the projection. Here is the maximum intensity projection, and now we will apply the protocol. So yeah. And here are the foci. I will not lose your time to select all of these foci. I will proceed to the next analysis that we need to do with our data. So when the image information, the whole images are already measured, and we will open a different tab in our software that allows us to actually visualize the whole repeats of the single experiment. So here we usually have more than 50, even sometimes hundreds of repeats of the same experiment. What you can do in this tab, you can do some standard normalization. For example, now I'm normalizing the data from 0 to 1 to be, and like this we'll remove the effect of the different expression of the protein in our cells. And now we will proceed to the mathematical modeling. We will use S4fit. This is actually a model that is this is a submodel that is derived from the model that Stoyno just explained you. This is a consecutive chain reaction model that can be applied for exactly this type of proteins that are recruited from to the DNA damage site by more than one reactions. So this means that we have a previous reaction to our reaction, in which our protein is taking part. And this formula can be applied directly to our software. From here, you can put whatever model you want to have. So this is just our model, but you can put here, for example, single exponent or whatever you want. And also we have an if statement inside this form that allows you to actually put some, for example, some step in which something is changed in the system. For example, you're putting some drug inside the system that will interfere the system. So you apply some model to some point, and from that point you apply a different model. And now, what will do our software? Here are all variables that will be changed when we press the solve button. So our solver will start to solve this function for every time point and to trying to find the optimal values of these variables that will represent as much as possible the data. So we'll put some starting values, for example, here 0.1, 0.2, 0.3. So this is the curve that I put with random numbers. Now I will press the button solve, and the solver calculates some curve that is trying to feed the data. So this can be stored to our software. I'll call it all proteins. Something that is also very useful now, no matter how many repeats we have for these experiments, so here we can have hundreds of different series. So this one, this one, this one, they can be hundreds. You can press just a button solve repeats, and it will apply these parameters for every single repeats, and it will try to solve the model for every cell. And if we look, here is the solution for these 4 cells. So if we have enough repeats, this line here is going to become more smooth, and I'll show now experiments. This here, you can see how smooth is it. So these parameters, they are very useful because they are showing, these parameters actually are rate constants, so they show us the speed of the reaction, and we can use this information to compare this protein to different proteins that are participating in the DNA repair. Our software was developed to analyze this exact type of experiments, but now it is growing, and actually you can put whatever you want image in the software, including even images from your smartphones, for example, and you can try to analyze them. And it is currently opening most of the available microscopy file formats. So if someone of you decide to use it, maybe I hope there will be no problems with opening with the opening of the files. And you can use it for different types of experiment, not only for micropoint. You can track, for example, DNA repair foci. You can do some FRAPA measurements. For example, here I can show you modeling that we did on the FRAPA curve. We have a predefined models for the reaction diffusion equation. So you can fit to pure reaction, to pure diffusion, to reaction diffusion equation in our software directly the data. And you can obtain the parameters, the kinetic, the K off, K on, the diffusion constant from here. And yeah, as you can see, the image analysis is very important because for example, in our images, we usually have more than 1,000 frames for a single image that our microscope obtains for a single hour. And you can imagine that this is growing up to tens of thousands of images per day. And if someone tried to just manually circle some regions of interest in order to measure it, this will take really a lot of time. And because of that, we invested time to develop this software to improve the quality and the speed of the analysis. And this make possible the analysis of huge amount of proteins for very little time. So, our software is actually an open source, so the source code is publicly available in GitHub. You can check our website. There is documentation available for we have tutorials how to use the software. Also, the source code is very nicely commented, so you can easily use some fragments of it. So if you have any questions, thank you for the attention. And, yeah. Yes?
What information can we obtain by measuring the average area of the spot after the radiation?
The mean value actually is providing the average value of the intensity of the pixels inside the region. So this means that for example, we can have intensity of 100 and intensity of 200 pixels inside. This is the maximum and the minimum. They're usually like a Gaussian curve, and the mean value is actually the average of all the pixels inside the row. Yes?
So when you're tracking the area around, from time point to time point,
Yes?
does it ever move, like its size in a frame? So is it hard to match which?
Yes, I can show you even one video now. Here is more complex, so I'll open directly the processed one. Here we have a cell that is actually entering cell division. So you can actually track the both cells during the time and measure what is happening there.
And for the spots,
Even for the spots?
for determining which spots went to which ones before.
Yes, it is tracking and finding the closest cluster. So it is obligatory to be just a small movement.
Okay.
It cannot, for example, detect the movement from, for example, 2000 pixels on the left, but it is searching for the closest cluster to the one that we detect on the previous to the previous frame.
And like does it apply like some cutoff for how big the thing has to be?
Yes, yes. You can filter minimal size, maximal size. This is something that you can specify from the software here. You can put the maximal speed that can have the cluster, the minimal size and the maximal size of the cluster.
What language is the software?
The language of the software is C#. Yeah, and it's actually built it from scratch. So we didn't use almost any external libraries.
What kind of hardware does this use on the calculator?
It can, this software now is running on this machine, so it's using only this computer. It's not using some cluster. Yeah, it's using only the CPU. We use the GPU for the visualization because actually in the middle of the screen, this is actually an OpenGL control. So it's these images are drawn by pixels. It's using the graphical card to increase the speed of visualization. Yes? So if the algorithms succeed to segment the image, you can apply it even to in vitro data. Yes, the point is, can we segment the image? So we need first to be able to visualize the separated cells and to segment them in order to analyze them. But we cannot, we never use it, for example, for some C. elegans or something like this. We never use it to measure such an experiment. We use it only for cell lines. You can track it, yes.
If it's image, you can actually see it. And use it and do it whenever you want to model it.
Yes. Also, it is not obligatory to use the image analysis part to use the modeling part. So if you have tab delimited or CSV delimited text files, you can directly use only the modeling part and the results extractor tab. There are no questions. Thank you.